We want to calculate the acid dissociation constant for formic acid, given that we have an initial solution concentration of 0.10 moles per liter and an equilibrium pH of 2.38. To start with, let's write down the acid dissociation constant equation, which is generically H3O plus times A minus over HA. The dissociation of formic acid we can write down as HCOOH in aqueous solution reacts to form hydronium ions and formate ions. So we can now complete the acid dissociation constant equation using the actual species involved in this reaction. So we still have H3O plus as one of the products, but now instead of A minus, we have HCOO minus, the formate ion, and instead of HA, our molecular acid is formic acid, HCOOH. So we can see from this equation that in order to calculate the acid dissociation constant, we need to know the concentrations of these three species at equilibrium. And the easiest way to determine this is using an ICE table. So we have three molecules of interest here: formic acid, hydronium ions, and formate ions. And we want to know the initial concentrations, the change in concentrations, and the equilibrium concentrations. So ICE, initial, change, and equilibrium concentrations, all in units of moles per liter. Now that we have our table set up, we can start filling it in. We are told that our initial concentration of formic acid is 0.10 moles per liter. We do not have any hydronium ions or formate ions when the reaction begins. We are not given any equilibrium concentrations, however we are given pH. And we can calculate hydronium ion concentrations from the pH. H3O plus concentrations equals 10 to the power of the negative pH equals 10 to the negative 2.38, and that is 4.17 times 10 to the minus 3 moles per liter. So let's fill that in. The equilibrium concentration of hydronium ions is 4.17 times 10 to the minus 3 moles per liter. Now it is very simple to calculate the change in hydronium ion concentration. That is simply the equilibrium concentration minus the initial concentration, which is 0. Therefore, our change in concentration is the same as the equilibrium concentration, 4.17 times 10 to the minus 3 moles per liter. Now that we have filled in the column for H3O+, we can start working on the columns for formate and formic acid. So looking at the equation up here in the top right corner, we see that the stoichiometry is 1 to 1 to 1. This means that for every molecule of formic acid consumed, one ion of H3O+ and one formate ion will be formed. So we could write delta H3O+, right, the change in hydronium ion concentration, is equal to the change in formate concentration, and is equal to the negative change in HCOOH, or formic acid concentration. Since both hydronium ions and formate ions are being formed, and formic acid molecules are being consumed. So now we can fill in the numbers for the changes in concentrations of HCOO- and HCOOH. The change in concentration of formate ions is the same as the change in concentration of hydronium ions. That is 4.17 times 10 to the minus 3 moles per liter. The change in formic acid concentration is the negative change in hydronium ion concentration. So that is negative 4.17 times 10 to the minus 3. Next, we just need to determine the equilibrium concentrations of formate and formic acid. So equilibrium concentration is equal to initial concentration plus change in concentration. So we add up those two rows. For formate, 0 plus 4.17 times 10 to the minus 3 is 4.17 times 10 to the minus 3. Now we actually have a tiny bit of math to do for formic acid, and I'm going to write that out because there's a little trick we can play. So we can say that formic acid concentration at equilibrium is equal to the initial formic acid concentration plus the change in formic acid concentration. We can put some numbers in here. 0.10 moles per liter is the initial formic acid concentration, and the change in formic acid concentration is negative 4.17 times 10 to the minus 3 moles per liter. 0.1 minus 4.17 times 10 to the minus 3 is 0.0958. And we could write that down in the box for the equilibrium concentration of formic acid, but we can also look at that number and say, you know, that is actually really close to our starting concentration of 0.10 moles per liter. And we can often make that assumption. When you have a weak acid, it does not dissociate fully. In fact, it often does not dissociate very much at all. So effectively, you do not see a change in its concentration. So we could actually just write down that the equilibrium concentration of formic acid is the same as the initial concentration. Well, now we have all of our equilibrium concentrations filled in, and from that we can calculate Ka, or the acid dissociation constant. So let's write down our equation for that. So Ka is equal to the concentration of hydronium ions, and we determined that that was 4.17 times 10 to the minus 3 times the concentration of formate ions, which is also 4.17 times 10 to the minus 3, divided by the concentration of formic acid at equilibrium, which we are saying is 0.10 moles per liter, that there was no change from the initial to equilibrium. And if you are unsure about that, you could actually use the value of 0.0958 in the denominator there and see if you get the same answer as we get using 0.10, which is 1.7 times 10 to the minus 4. That is the acid dissociation constant for formic acid.